Wow, my laptop actually connected to something. Excellent. So yeah, this is joint work with my PhD supervisor, Alan Mycroft. I'm going to be talking about the system we have for doing type inference and subtyping while having ML-let polymorphism. So I'm going to start off by giving a demo rather than making you sit through 20 minutes of Greek letters first. So here we have two records. The first one has a Boolean, which apparently is on fire, and both of them have an integer size field. Then we write a function which chooses between the two of them. Oh, okay. Can everyone see them? Is that legible? Okay, so here's a function which chooses between both of them. So in this system that gets the type, it takes a Boolean and it produces a record which has a size field. If we try to do something similar in OCaml, then, so here we're using objects as records. OCaml does have a full object-oriented system. I'm just using them as records for the moment. Then it tries to unify the two types, and one of them has an extra record field. So by allowing subtyping, we can use values with different sets of fields, different features, without having to worry about whether they're exactly the same. But so this sort of thing can be done in languages like OCaml with enough annotations. The interesting thing here is when we get subtyping, we actually get more polymorphism, even out of functions that you can already write in OCaml. So supposing we write a predicate. So this predicate applies to one of those objects, but does not apply to the other. As you can see, we have research quality type error messages, which are both accurate and concise. So then we write a function, and this is just a pure ML function. There's no record object funniness going on here, which chooses between a value and a default by looking at a predicate. So select of predicate value and default goes, if the predicate holds the value, then we use the value. Otherwise, we use the default. So this is like no weird objects going on here, just a fairly straightforward ML function. And OCaml or any other ML tells us that the predicate is an alpha to bool, the value is an alpha, the default is also an alpha, and the result is an alpha. So this is a little bit strange because it's demanding that the default, a thing which we never actually pass to the predicate, must be of such a type that we could pass it to the predicate. So this means that while select with the existing predicate x and y is a fairly reasonable thing to write that would not go wrong at one time, because it's going to check a predicate on x and return one of the other objects, we can't write that in a language based on equalities, because it sees the data flow going one direction and going the other direction, and since it's only got equal signs, it loses track of which direction things are going. Whereas when we have subtyping, we can write exactly the same function, although again, because of a research quality parser, we have to write it slightly more long-windedly than you'd like. And we see that here, actually I might just make that wider so we can see the whole line. Here, this takes the predicate, which is an alpha to bool, and forgive the extra brackets, research quality, pretty printer. It takes the value, which is an alpha, the default, which is a beta, maybe a different sort of thing, and returns the upper bound of alpha and beta. So in this case, we can write select between those two, and x is a thing that can be passed to the predicate, and we get back something which is the upper bound of x and y, which only has the fields common to both. Okay, so it's not just about like being able to use object-oriented features or records or whatever. It's about getting more polymorphism out of functions that we could already write. So, okay, now I'm going to talk about how this actually works. So this is traditionally considered hard. There's been a chunk of research on these kind of problems. And rather than actually solving the problems raised previously, I'm going to do the best to avoid them. So the first one is picking a different definition of types, which sidesteps some technical issues. And the next thing is just not bothering to use most of them. So first I'm going to talk about the actual definition of the types. So this is a fairly standard definition of types of subtyping that you'll see in many, many papers. We start with the monomorphic types. We say a type is either the bottom type, the subtype of everything, the top type, the supertype of everything, or a function. Next, we add some subtyping rules. We say bottom is less than any type is less than top, and functions are contravariant on their domains and covariant on their ranges. Okay, and this actually turns out to be quite a well-behaved structure. We just defined an order there, but it turns out to be a lattice for any two types. There's a least common supertype and a greatest common subtype. And there's quite nice algebraic identities like the one below, which hold for it. So this is a fairly well-behaved structure, which is presumably why it appears over and over again in a long string of papers. And then we try to introduce polymorphism and particular type variables. And we end up with questions that just have no right to be this difficult. So here's one example of just a simple question involving polymorphic type variables. Is this true for all alpha? And by applying the subtyping rule, we can see that it is. It splits into two cases. Alpha is less than top and bottom is less than alpha. This is true for all values of alpha. And this sort of question comes up all the time when we're trying to do type checking. We're trying to type check. We're trying to check a subtyping relationship between two terms with variables in them. And then we see more complicated and fiddly examples. This example is actually from François Patier's PhD thesis. There's various other ones in the literature from papers by Joe Himnier and Tim Poisonetz and others. And they're just monstrously difficult for no apparent reason. This one turns out to be true. You can prove that it's true by doing case analysis on alpha, by checking for alpha equal to top, then alpha equal to bottom, then alpha equal to some function. And in each case, it works. And it turns out, in a way I'm going to explain, it is only true by case analysis. So I would like a type system to be extensible. If the program type checks and we add more types to the system, it shouldn't cease to type check. Programs shouldn't be invalidated by adding more junk into our type system. This is useful because as language designers, we're in the business of adding more junk into our type systems. Users are often given to adding more junk to the type systems, and when we separately compile files, we don't know about all of the junk when we're compiling one of them. And the system I just described, with types being defined by just monomorphic types and quantifying over them, is not actually extensible. Supposing we add a new type of functions with these squiggly arrows here, which is a supertype of the previously existing type sort of functions. So we can think of these as functions that may fail to terminate, or functions that may do a side effect, or something that's more general than the normal sort of functions. And we haven't changed any of the subtyping relationships between previously existing types, and we haven't even changed the lattice order. The meets and joins of previously existing types are exactly the same as they were. And yet, using this new type constructor, we have a counterexample. So this example here relied on the non-existence of this certain type and is invalidated by adding more things. So this example and other examples were previously used to demonstrate that the problem of deciding these relations was hard, or that a particular algorithm was incomplete because it didn't manage to cover this particular case. I think these examples should be used to say that maybe this is not the right definition. We should define types in a way that has an open world definition, doesn't assume a fixed set of types, such that these sort of examples are just false. Rather than being the edge cases that the algorithm can't handle, they're just things which are false because they have counterexamples in some suitable extension of the system. So I'm not going to go into great details, but there is such an open world definition. It's actually quite straightforward. You just, instead of starting with monomorphic types and quantifying over monomorphic types, we have type variables and meet and join operators in from the start and quotient by which terms should be equal. It's the standard construction of a free algebra, and it doesn't, in particular, things like alpha and beta are added fresh and not assumed to be equal to other things. So in this system, hard cases like the one at the top of the slide there are simply false. And deciding whether a subtyping relationship holds between terms with variables is much easier and is essentially the same, more or less the same algorithm that was known 20 years ago as a sound but incomplete algorithm. It's the cases where it is incomplete are cases that I don't think we should count as true at all. So the next trick is only using half of the types. We introduced these operators of this thing, which is the upper bound of two types, like essentially think of it as or union. It's more like the type of which both of them are a subtype. And similarly, we have a meet operator, which is the greatest lower bound of two types. These only come up in certain places. If I have an if some condition produces something of type A, otherwise produce something of type B, then the result is going to be either A or B. It's going to be the upper bound of A and B. If I have a function which uses a variable x and uses it once as an A and uses it the second time as a B, then it's going to want the input to be A and B. But this operator, the join operator, only appears positively describing outputs. And the dual, the meet operator, only appears negatively describing inputs. So we apply a syntax restriction where we divide types into output types and input types, where only the output types can have the union operator, or the join operator, only the input types can have the meet. And then we only use these type check programs. So this seems like it might interact weirdly with polymorphism. We're used to seeing like polymorphic functions like this one, which takes two values and returns one of them. And the way you do it in ML is you substitute the same value, the same type, into all locations. So with subtyping, we can use these functions a little bit more generally. We don't have to put in exactly the same type in each location, because we can substitute in and use subtyping to change some of the types. In ML, the type you put in for the positions 1, 2, and 3 must be exactly the same. But with subtyping, whatever you put in as 1 must be a subtype of 3. Whatever you put in as 2 must be a subtype of 3. There need not be any particular relationship between 1 and 2. They just must both be subtypes of 3. So the way we handle instantiation of polymorphic terms here is we don't have to put the same type in for each occurrence of the alpha. We put a negative type in for the first occurrence, a different negative type in for the second occurrence, and some positive type in for the third occurrence, such that the two negative types are both subtypes of the two positive types. So we have this syntax restriction, and this is how we can maintain it through let polymorphism, MLsub polymorphism. But what does it actually buy us? What do we get from being able to restrict things in this fashion? So when you implement Hindley-Milner inference, which I now know should be Newman-Curry-Hindley-Milner inference, or perhaps Newman-Curry-Hindley-Damas-Milner inference, and so on. We unify in there are various different occasions which we run the unification algorithm. We could be using a type variable in scope in two different ways, and we unify two types which are inputs. We could be unifying two different results, two different branches of the computation, which are unifying two outputs, or, as comes up in the application rule, we could be using the output of one expression as the input to another expression. So if we apply our syntax restrictions, then we find that the first case in unifying two input types is when we combine two negative types with the meet operator, which satisfies the syntax restrictions. The second case is when we combine two output types with the join operator, which also satisfies the syntax restrictions. And in the third case, which is the point of all of this, the subtyping constraints that we have to look at are only ever positive type, subtype of negative type. Because we're only ever, the third case here, the only interesting one, is when we're feeding the output of some subexpression to the input of another. So, how do we decompose those constraints? In particular, how do we deal with these awkward lattice operations, the meets and joins, which are the things that we don't have in ML? Well, when we know that they're in this form, it's a positive thing on the left and a negative thing on the right, they're actually very easy to deal with. Join on the left of a subtyping relation splits into two things. Join of T1 and T2, subtype of T3, is equivalent to T1 subtype of T3 and T2 subtype of T3. So it's just essentially another case of the unification algorithm as we go breaking down type terms. A meet on the right is equally easy to deal with. T1 less than T2 and T3 is T1 less than T2 and T2 less than T3. Or sorry, T1 less than T3. The difficult cases are having a meet on the left or a join on the right. But by maintaining these syntax restrictions through inference and polymorphism substitution and the entire point, maintaining through every stage of type checking, we can guarantee that they never come up. Okay, so we built a type checker and type inference system, along these lines, and fed it the OCaml list module, which is a convenient source of higher order functions. So most of it type checks. Again, the parser for this language is rather stupid. So for instance, I can't write this, but I can write this because simply haven't implemented most of the cases. So we had to mangle the syntax of the OCaml list module a little bit to fit into this. But after having done that, all of the functions type checked, except for the ones using arrays or other things we hadn't implemented, and actually had the same types for almost every function except for the ones that used polymorphic equality. That they were actually, like for instance, we can write map. So map takes a function and a list. Sorry, I need to do back. And I'm not quite sure what that was about. So this actually has exactly the same type as it does in OCaml or any other language. It's just because of subtyping, we can use this type in slightly more interesting ways than we might normally be able to. This website is, that demo was the type checker written in OCaml compiled to JavaScript. It's online. And there's a longer version of the 2-page paper for this available there. So, questions? No?
I have another question. First of all, you don't have explicit quantifiers for your types. It's A or B. Implicitly. That's bad. Fix it now.
I agree.
And the question is, so if I understand correctly, when I your slide of polymorphism, when I have a outer variable input and output, on the left I get only pass a negative type. So if as a user I want to associate this with a union, I need to choose which of the two types I want. So you said it works for a type to be smaller than the union. But how does that happen?
So there are essentially no situations where you would want to put a union on the left-hand side of an arrow or in a negative location, because how could you possibly use this? What could you pass to a thing requiring such a type? You would have to know that, like, if there were any features in common which allowed you to pass something to there, then you could write down those features not involving the union.
So I'm just trying to make sure I understand correctly. If you go back to the example, we have the actual code.
Yep.
So you have to do the X and the Y, right? Sort of records.
Yep.
And then with the big one, it chooses the size and just uses that as the output as the result. But how does it know that if for example X had two integer records, how will you know which one of those to pick? Or sort of, if there is,
So
there, if you had like a size 2 and that was 43, how does it know to choose in the pick one?
okay, so an easier way of doing this is to make pick one be parameterized over what X and Y are. So then we can see that so pick one takes two things of type alpha and returns an alpha, which is actually equivalent to taking an alpha and a beta and returning their upper bound. It's the only thing that matters is where the constraints are. It just takes. So actually, let's just say we specify one of those. So we fix X to be the type of X there and take Y as a parameter. So this is going to take Y as a thing of type alpha, and a Boolean, and it will return something which is the upper bound of a thing like X and whatever alpha happens to be. So the upper bound of two record types is the thing that has the intersection of the fields, like whichever fields are common to both, with the upper bounds of their types. So for instance, we could have, like, y could have size 2 equals whatever. And then we get, sorry, and if we actually pass y explicitly to this, then it just gets whatever fields are common to the two of them.
Okay, so you match up the name.
Yeah, sorry, it's structural subtyping. It's based on the names of the fields. Yeah.
With traditional subtyping constraints, it's the complexity of satisfiability is quite high. It's cubic time. I was wondering what's the complexity here, or is it better?
No, it's essentially the same. So it's cubic time, although you need to be, as with previous work, you need to be doing some interesting things with recursive types before you can get into the really slow cases. I'm not sure, but I think you may be able to give a better bound for cases where you know it's not recursive. So yes, I didn't mention this talk, but there are recursive types in this system because in ML you can choose not to have recursive types and not break any programs because either a program is typable with recursive types, or it's if a program is typable with finite types, then all of it has a finite type, it doesn't have a recursive one. But with subtyping, there are programs which have finite types, but whose principal type is a recursive type. So you can't just ban recursive types without losing principality.
Does that mean that every term is typable?
Yep. So self-application is actually semi-reasonable. It's a thing which demands that its input be both an alpha to beta and an alpha, and it returns a beta. And then, this is great fun. This is correctly a non-terminating program, although the typing derivation requires recursive types in the middle.
Do you have examples that are usually typable with the traditional subtyping approach and that we
So involving type annotations, yes. So the main difference is that in this system, it's much easier to, well, firstly, you end up with reasonably compact types rather than producing a graph of subtype terms. But secondly, the types can actually be compared reasonably easily, at least, like, it is decidable. It's not even undecidable for previous systems. So while the untyped programs that can have types ascribed are the same, if the user writes an annotation, that can be checked with the system. Without annotations, it's the same, yep. Yeah?
Your problem with the open world assumption versus the closed world assumption also appears in the semantic subtyping world. There are at least a couple of solutions. I don't think any of them corresponds to yours. I think yours might actually be better.
Yeah, so there's a yes, a lot of the semantic subtyping work is the similar approach of, like, basically not liking the previous definitions of subtyping. That work is more going for set theoretic semantics and a very expressive type system where it can, like, express very fine distinctions between different sorts of types, and often systems with type case. So you can have a function which examines its input and decides what type it is. Whereas I'm going more for a system that gives simple enough types that inference is reasonable. The types in most of the semantic subtyping work are so fine and sophisticated that you've no hope of actually inferring them and making them be reasonably compact.